Hi everyone, my name is Geng Chen, an undergraduate student from Shanghai Jiaotong University. Now I'm presenting our paper Continual Predictive Learning from Videos. I and Wenlong Zhang are the first authors of this paper, and Yunbo Wang is the corresponding author. Predictive learning is an unsupervised learning technique to model visual dynamics, and the learned world model can be used in various visual control tasks, for example, robot manipulation. Existing predictive learning methods usually assume a stationary environment with relatively fixed physical dynamics. However, real-world environments can be highly non-stationary. Therefore, existing methods may underperform due to severe catastrophic forgetting problem. For example, if we first train a video prediction model PredRN for task hammer on the meta-world benchmark, it can generate satisfactory results. However, if we continually train the model on task assembly and task sweep, the result for hammer quickly deteriorates. To study the predictive learning problems in non-stationary environments, we introduce a new research problem, continual predictive learning, in which prediction tasks arrive sequentially during training periods, nor only few data from previous tasks can be saved, and the world model is expected to handle both newer tasks and older ones after the entire training phase. For example, in the continual meta-world benchmark we propose, the robot is expected to learn the prediction task of hammer, assembly, and sweep sequentially. The main challenge of continual predictive learning is due to the coexistence of three types of distribution shifts: the covariate shift, the target shift, and the dynamic shift. The covariate shift of input data is considered by most existing continual learning methods. However, in continual predictive learning, the generated target frames and the spatial temporal dynamics also change over training periods, leading to the target shift and the dynamic shift, which are new challenges in continual predictive learning. We evaluate the video prediction method PredRN and its combination with the classic continual learning method EWC on the continual meta-world benchmark, and demonstrate the result for both the first task hammer after each training period and the results for each task after training on the last task sweep. The results show that both methods suffer severe catastrophic forgetting problem in both appearance and motion due to the covariate dynamics target shift, while our method CPL is always able to predict in consistence with ground truth. We also conduct experiments on the robotic benchmark RoboNet and the human action benchmark KTH in a continual setting, and compare our method with existing video prediction methods and their combinations with classic continual learning methods. The left side shows the qualitative results on KTH benchmark for the first task boxing after training on the last task running. Our method is the only one to predict the right action. The right side is the average quantitative result on each task after the whole training phase, and our method significantly outperforms the other methods. Finally, we evaluate all the methods for each task after each training period, and the results show that our method can effectively mitigate catastrophic forgetting and remarkably outperforms the other methods in all training periods. Our approach CPL composes three main components: a mixture world model for task-dependent feature frames prediction, a predictive experience replay scheme against catastrophic forgetting, and a non-parametric task inference strategy. Below is the overall training pipeline using the predictive experience replay scheme. In the first task, the world model M is jointly trained with the generator G, which learns to generate the first frame of videos. And in the following tasks, we use G to generate the first frames of previous tasks, then use the world model M to predict the corresponding future frames, and finally combine the rehearsed data of previous tasks and the real data of current task to jointly train M and G. To further explain the mixture world model, it is a new recurrent network that captures task-specific visual dynamics. Unlike existing world models, the learned price informs a mixture of Gaussians to overcome the dynamics shift. Finally, since the mixture world model requires the task label, we propose a non-parametric strategy to make task inference at the task time. In the future, we plan to extend CPL for real-world model-based reinforcement learning problems. Thanks for listening.